So, welcome back student for the next class of this linear vector space. In the previous class, if you remember, we defined two very important concepts. One was spanning set and then we also defined something called basis. Now, if in a vector space, what is basis? Let me recall it. So, say E1, E2, En are the set of n vectors which are linearly independent to each other. They are linearly independent. Then any vector, this is a set of vector from a vector space V, say. So, in this V we have many other vectors. Any vector x, for example, that is in this vector space can be represented as a linear combination of this, like x1 E1 plus x2 E2 plus xn En. x1, x2, x3 are essentially the scalars or the components, and E1, E2, E3 which are linearly independent set of vector, we call it as basis. Now, I changed the notation. This notation has already been introduced to all of you, that this is a very important notation in the context of quantum mechanics, and we call this as a Kate notation, or sometimes it is called Dirac notation also. Now, the next question is, also we define something in terms of this n tuple notation. Say E1 is, if I say this is a n cross 1 column matrix, and in this way if I represent En, which is something like, and this is another notation which is the n tuple notation, and any vector, if I write the vector in this form, then x1 multiplied by 1 0 0 plus x2, right hand side I write x is my vector, then x2 is 0 1 0 0, then x3 is 0 0 1 0 0 up to n term, and so on up to xn, which is 0 0 1. This is the most natural way to express a vector. In the right hand side, if I write the vector will come out to be simply x1 x2 xn in a component form. This basis one, these are called natural bases. Last year we also discussed these things. Now, in terms of this natural basis, we can expand a vector as well as the matrices. So, let me just briefly describe how a 2 by 2 matrix, say A, this is for to note that how the basis is working, natural basis is working. So, if this is a 2 by 2 matrix which is also B, a element of this vector, so we can also expand this matrix A in terms of its basis vector. So, what should be the basis of a matrix? It should be something like this. So, I can figure out a few matrices like this 1 0 0 0, then 0 1 0 0, 0 0 1 0 and so on, and this, since this is a 2 by 2 matrix, I can define these matrices through which I can decompose the entire matrix elements. These things now work as a basis. These things are now work as a basis, and not only that, it is a natural basis. Any matrix I can expand in this form. So now I have an idea that how the natural basis is working, but there are more important things related to basis. So let me go back to our one dimensional case, 1D. That means I have only one direction, say x. So now the question is, if I have one direction, one dimensional thing, then how many linearly independent vector I can find? This is a very important question, that how many linearly independent vector one should expect for one dimension. For example, if I write a vector like this, say this is my alpha, which is a vector in this direction. If I want to write another vector in this direction, say beta, I can always write beta in terms of alpha. Beta is nothing but some multiplication of alpha. Beta is nothing but some multiplication of alpha. This is just increasing the vector beta, and if I multiply by suitable value, then I can have beta. So that means alpha and beta are not linearly independent, they are dependent to each other, because if I write this equation in a different way, I will go back to my original linear combinations, and I find that a vector, if you remember this notation, C1 alpha 1, C1 alpha 1 plus C2 alpha 2 plus Cn alpha n is 0, and if only solution C1, C2, C3 is 0, then these vectors are linearly independent vectors. But here we have already find a condition where A is not equal to 0 and there is 1, so both are not equal to 0, but still I am having a condition that this is 0. That means I have a non-trivial solution for C1, C2, C3, where 1 and minus A are two values of C1 and C2 if it is taken up to two dimension, right, two components. So that means I can have a non-trivial solution, so these vectors are linearly dependent. So that means in 1D at most I have one linearly independent vectors. So 1D, I should note that maximum linearly independent vector is equal to 1. Go back to, now let us try to find out what is happening in case of 2D. So 2D, in 2D I have x and y, this is my 2D plane. In 2D plane, if I have two vectors like this and this, I call it this vector alpha, I call this vector beta. So there is no way that I can write alpha in terms of beta. So that means essentially alpha and beta, these two vectors are linearly independent to each other. We can also show that in a more general way. So let me do that. So now we have a note that in 2D I have at most two vectors which are not depend on each other or linearly independent, but I can do that in a more convenient way. So I will go back to this. So this is say my beta vector, this is say my alpha vector, which are in two dimensional plane. Now what I will do, that I will make a vector perpendicular to this vector alpha. I called it alpha perpendicular vector. When I make perpendicular to alpha vector, then I can always write this equation C1 alpha plus C2 alpha perpendicular. If it is 0, I am using entirely I am using the K notation to make you familiar with this notation. You can do that in the same way by putting the normal vector sign. It will not going to make any difference, but it is better that you should learn this notation also. So now if I have this expression in my hand, since these and these vectors are perpendicular to each other, that means no way I can write this vector in terms of this vector. So only solution is C1 is equal to 0 and C2 is equal to 0. This is the only solution. That means these vectors are linearly independent vectors, that is for no doubt. But what about beta? I can now I need to find out this condition, A1 beta plus A2 alpha. If it is 0, my next question is it possible to show that A1 and A2 is also 0? Because I am claiming that these two vectors are linearly independent vectors, because these two vectors cannot be written in terms of each other, but I need to show that. So after considering this equation, I can show that it may be possible. So let me do that in this way. So beta, I know that this is a vector along this direction, can be divided into two components, this and perpendicular components. If I do that, say B1 alpha plus B2 alpha prime, these are the two components I can subdivide this beta, that I always do. After having the value of beta in this form, the next thing is I can put this here. So A1, I have this equation, now I am using this equation to this equation. A1 beta is this much, so let me write it, beta 1 alpha plus beta 2 B2 alpha perpendicular plus A2 alpha is equal to 0. In terms of alpha and alpha perpendicular, I write the entire equation, which is this. Now I can also write this equation by rearranging the term in this way. Now if I look this equation, say this is equation 2 and my first equation 1, this essentially both the equations are same equations, C1 some constant multiplied by alpha, C2 some constant multiplied by alpha perpendicular, here also I have something multiplied by alpha. So I can consider this as my C1, I can consider this as my C2. Here one thing also you should note that since I am subdividing beta into two parts, so this B1 should be not equal to 0 and B2 should be not equal to 0. Both are not equal to 0 simultaneously unless beta is a null vector. I am not dealing with the null vector right now. So that means this equation C1 and C2 are 0 already we figure out. So from that I can say from first equation A1 B1 plus A2 is equal to 0 and A1 B2 is equal to 0, because A1 B2 is nothing but C2, A1 B1 plus A2 is nothing but C1, both are 0 I have already figured out. So now this is 0. With the condition B1 and B2 not equal to 0, I can also say that if this is not equal to 0, A has to be 0 to satisfy these things. So A1 is 0, one condition I figure out. If I put A1 is 0, then naturally it comes that A2 also has to be 0. So now A1 and A2 both are 0, it is the only condition that we find. So here if I find this equation which I try to find out, we can readily see that this is possible only when A1 and A2 are 0. And what is essentially means? Essentially means beta and alpha are linearly independent vectors. So two linearly independent vectors can be possible in 2 dimension. So this is also an important outcome that step by step we are going. So first first equation we have already find, first conclusion that in one dimensional maximum linearly independent vector should be 1. In 2 dimension I can extend this comment that maximum linearly independent vector one can have is 2. What about 3D? Now you can understand what actually I am trying to do. In 3D, if I write this as my x coordinate, y coordinate, z coordinate, then x, y, z is a 3 independent direction. So, this vectors, unit vector along this, if I write it is as E1, unit vector along this if I write it E2, and unit vector along this if I write E3 are the 3 independent direction vector which are not related to each other, they are linearly independent. So, any fourth vector, say R, this is my fourth vector, R can always be represented in terms of E1, E2 and E3. So, I can write it readily that means this equation E1, E2, E3 are all in the vector space. So, this equation one can modify and write in this form. Just to show the way it is defined for linearly dependent independent vectors. 0. So, now I have this is 1, this is minus R1, this is R2 and R3. So, I have a value if I say this is C1, C2, C3 and so on. So, for non C1, C2, C3 is not equal to 0, I am having a solution. So, that means if I use 4 vectors, then there will be a linearly dependency among them. So, maximum linearly independent vector in 3D is how much? There will be 3. So, again I have this for 3D, I have maximum linearly independent vector is 3. Now, is the time that we can generalize the thing. So, for 1D I have 2 linearly independent vector, for 2D I have maximum 2 linearly independent vector, for 3D I have maximum 3 independent vector. So, there is a intimate relationship between the number of maximum linearly independent vector that one can find in a space and the dimension of the space. So, if dimension of the space is n, then we can readily conclude that the number of maximum linearly independent vector in that space will be equal to n. So, in n dimensional space I can have at most maximum n number of linearly independent vector. I should not have more than that, because if I have more than that vector, then what happened, that vector can be represented in terms of other linearly independent vector. So, that we have already shown for 1D, 2D and 3D cases. Okay. So, now after having this important conclusion, now let us go back to another important topic which I mentioned in the last class, which is inner product, because there is a relationship between these things E1, E2, E3. Last day I mentioned also that if E1, E2, En are the vectors, then there is a relationship that they are orthogonal. We call it orthogonal. Right now I am not writing anything because I am not defining anything right now, but you should know that they are orthogonal, which is important property. The orthogonality property only we can define or only we can understand once I learn the inner product thing. So, inner product is already you know for normal vector, but this is not the fundamental. For fundamental understanding, we need to know few things more. So let us do that. Okay, so very important concept. Conceptually, you should understand this what is happening, which is called dual basis or dual space for the time. So dual space. What is dual space? So if we have a vector space V, then associated to vector space I can construct or have another space, I write it as V tilde, which I called dual space. Now what is the speciality of dual space, what it will do, and what contain, I mean what kind of things are there in the dual space. So dual space is containing, it is a set of all linear functional it is a set of all linear functional. Now I defined, in order to define dual space, now I defined another new term, linear functionals. So that means in order to understand what is V tilde, essentially I need to understand what is the linear functional, because this is a set of all linear functionals. So what linear functional will do, let us try to first find, then again we will go back to and understand what is the dual space. So linear functional. Linear functional is essentially a rule. The rule suggests that if I apply, if say it is a rule, let me finish this and then I will make you understand. Linear functional is essentially a rule which we can apply on the elements in the vector space V, which are vectors, and as a result I am having something which is not a vector, rather scalar. So this is a mapping which gives vector to a scalar. So that means I am operating something over a vector with this rule, and as a result I am having something which is a real quantity or complex quantity. For the timing, let us consider this is a real quantity, that is scalar. You know that the scalar field can be constructed by the real quantity, real elements, real numbers, as well as the complex numbers. So here what the mapping is suggesting, it is suggesting that I will apply on the vector and I am having a scalar. This is the most fundamental thing. Next, it has two properties. If I apply, say inside the V, the elements are something like alpha 1, alpha 2, alpha n. These are the suppose these are the elements in the vector space which are vector. Now if I apply this function over two element alpha 1 and alpha 2 like this, it will be given as this is one property. That means I will going to add this vectors thing and then I apply the rule over that. Whatever the thing it will give, that means it will give this f rule which is applied over a vector will give something which is a scalar quantity. So I will take one vector from V, another vector from V, I will add them and apply the rule over that, and I will get a real number or a scalar. I will do the opposite thing, not opposite, I will do the different thing. I will take the vector alpha, operate that over the rule. I will take another vector alpha 2, operate that over the rule. I will have now two real quantity and add them. This equation, these things, whatever I am getting, and these things are same things. So this is rule number 1. Rule number 2 is if A is some scalar, if I apply this scalar multiplied by these things over that, it is same as this. So now I can understand what is linear functional, and this linear functional suggests that if I apply these two things over that, I will have two different quantities. If I apply this over that, I will also have a quantity, but A will be going outside. So, these two, with these two properties I can form the linear functional. So far whatever I am showing is nothing but the definitions, but with these definitions I will not going to understand anything. So, let me give you the specific examples of these things, then you will be understanding that exactly what is going on in linear functional. What is linear functional? So, let me start with two examples and then gradually I believe you will understand. So, example 1. Example is dot product. This is my rule, dot product is my rule. How it is working? You know that dot product, if I have one alpha vector, if I have one beta vector, then when I am making the dot product, that means I am applying a rule over that. Dot product is a rule that I am applying over that. Then what I am getting? A scalar quantity. Remember, two vectors are associated with that, I am applying a rule which I call dot product, and as a result I am finding a scalar. So, I will write these things in our normal notation. So, for example, in a vector space I have the vectors like alpha, beta, gamma and so on. I am applying the rule dot product, and when I am making the dot product from the left side, I need to note this alpha. So, I am noting that this is alpha which I am making, which I am operating over a element say beta. So, that means this is my operation, I am operating this. So, this will be a scalar quantity as I show here. Now, my rule 1 suggests that if I apply this over beta plus gamma, applying this beta plus gamma. So, in the right hand side what should I write? According to my rule, it has to be this plus this, whatever the rule I defined just before. So, now let us consider with this in our usual notation things. Maybe you will be facing some kind of uneasiness by looking this kind of things, but let me do that. So, alpha dot beta plus gamma. How I write this? I can write this alpha dot beta plus alpha dot gamma, no problem with that. If I do, then if I write in my notation, it will be like this. Alpha is operating over that, so I have beta plus gamma, and this rule I can simply write in this way. What about the next rule? So, first rule is okay. What about the next rule? The next rule you will now understand by yourself that if I do that, if I make a constant, if I make a scalar and then operate, it is nothing but scalar this. So, now if I write in the same way alpha in our normal notation, say I will making alpha over a scalar beta with a dot product, then it will be simply A alpha dot B. I can write it A alpha dot B, always I write in this notation this, and this one can write this one can write. So, two of the properties are fulfilling with the fundamental rule that if I operating this over that, I will having a scalar. It essentially means that dot product is following all the rules for linear functionals. So, dot product is a linear functional. So, with that today I will going to conclude that class. In the next class we also start with this, because dual space is a very important concept we need to know. In the next class, we will start from this and we will start from a new example. It is not that dot product is a only example, there are many examples which can follow the linear rule of linear functional. So, next class we will start another with taking another kind of rule which also follows the linear functional. With that, let me conclude that. So, see you in the next class. Thank you for your attention.